Hello everyone. Today we start chapter 6 on differentiation. Section 6.1 is about derivative. So the content of this section is to give a definition of the derivative of a function and then derive several properties for that notion. In particular, we will learn how to compute the derivative for various functions. Here, throughout this section, we let f denote a function from some subset A to a set of all real numbers. The derivative of the function f of c is given by the limit if it exists of the following expression. So f prime of c is equal to the limit when x approaching c of the expression f of x minus f of c divided by x minus c. So if you took linear algebra, then and calculus, then we know the geometrical meaning of the expression. This is exactly the slope of the line segment connecting CFC and the point XFX, as you can see in this picture. The line segment here is the yellow segment in this picture. So the expression is the slope of the line segment. What is the meaning of the limit then? Remember, the limit is the limit of the derivative is the limit of the expression. So imagine that you, let's see, getting closer and closer to x. Sorry, you letting x getting closer and closer to c, then the line segment here getting closer and closer in angle to the tangent line through the point C. That implies that the slope of this line segment approaching the slope of the tangent line. Because the derivative is the limit of this slope, the derivative, even this is essentially the slope of the tangent line through the point CFC. Let me give you an example here. Consider the function fx equal x squared. Then we have fx minus fc divided by x minus c equal to x squared minus c squared divided by x minus c. And using algebraic manipulation, we have x minus c, x plus c in the numerator, and then x minus c in the denominator. So we see that both the numerator and the denominator has the same common factor, x minus c, so they cancel out each other. That's why the limit of the expression is exactly equal to the limit when x approaching c of the expression x plus c. By what we learned from a previous chapter, this is equal to c plus c, which equal to 2c. So the derivative is given in terms of the limit concept, and this is very convenient because we spent a lot of time in chapter 4 discussing the limit concept. Now we need to apply that notion to a special case to compute the derivative of a function. And the following theorem is very, very important because it essentially relates the two fundamental concepts we learned in this class, differentiability and continuity. Recall that continuity can also be interpreted as a statement about limits. So it's not surprising that these two notions are related to each other. But how are they related to each other? Well, we have the following theorem. If the function f forms some subset A to the set of all real numbers has a derivative at some point C inside the subset A, then the function f is actually continuous at C. That's why differentiability implies continuity. In other words, differentiability is a stronger condition than continuity. And let me give you a proof of this theorem because it really illustrates how these two notions are related to each other. So we consider the difference fx minus fc. This expression appears frequently in the definition of the continuity concept. So this is about continuity. On the other hand, it can be written as fx minus fc divided by x minus c and then multiplied with x minus c. The expression inside the bracket here is related to the differentiability. So we can take the limit of both sides of that equation. On the left hand side, we have the limit of fx minus fc. On the other side, you have the limit when x approaching c of this product, fx minus fc divided by x minus c multiplies with x minus c. So by a theorem we learned in chapter 4, so the equality here follows from the theory we developed in chapter 4. This is equal, the limit of the product essentially equal to the product of limits. So we have the limit of this expression fx minus fc divided by x minus c, and then you have the limit x approaching c of x minus c. And you realize that the first expression here is really the derivative of the function. So this is f prime evaluated as c multiplied with this limit, which equal to c minus c So this is just equal to 0. Therefore, we obtain that the limit when x approaching c of fx minus fc is equal to 0. Again, by the theory in chapter 4, the left hand side equals the limit of the function f of x minus the limit of f of c. So the limit of the difference is the difference in limits, and it's equal to 0, which implies that the limit when x approaching c of the function f of x equal to the limit when x approaching c of f of c, which is equal to exactly f of c. So the limit when x approaching c f of x is equal to f of c. But this is exactly the limit definition of continuity. Therefore, the function f here is continuous. Let's see. And that is the end of the proof. So the proof here really based on that algebraic relation between two expressions, one corresponding to the definition for continuity and the other to the definition of the derivative. However, the converse is not true. That is, continuity doesn't imply differentiability. And here we give a counter example. Consider the function fx equal to the absolute value of x. It's easy to show that this function here is continuous. However, we want to claim that the function doesn't have a derivative. A c equals 0. How? The proof is based on the definition of the derivative. So we consider the expression f of x minus f of 0 divided by x minus 0, which is equal to the absolute value of x minus absolute value of 0 divided by x minus 0, which is essentially equal to absolute value of x divided by x. So for x bigger than 0, this expression equals 1. For x smaller than 0, this expression equals minus 1. Therefore, the left hand limit and the right hand limit do not agree with each other. That's why the limit when x approaching 0 of this function does not exist. And that's why there is no derivative for the function f of x at 0. So we just learned a very interesting connection between derivative and continuity. Namely, differentiability is a stronger condition than continuity. Differentiability implies continuity, but the converse is not true. Now we're gonna learn several basic properties of derivative. So the fundamental theorem here basically tells you how to compute the derivative combination of functions. We learned from a previous section that we can construct new functions by combining certain standard fundamental functions. That's how we come up with so many different functions. Based on that observation, we see that as long as we know how to compute the derivative of these fundamental functions and know how to compute the derivative of a combination of functions, then we should be able to compute the derivative of every function. So this is very common in mathematics. We're trying to develop a general rule that is applicable in a wide range of applications. So going back to this theorem, let I be an interval inside the set of all real numbers. C is an element in this interval I, and f a function from I to R, and G another function from this interval I to the set of real numbers R. Let us assume that these functions are differentiable at some point C. Then we have the following. If we multiply the function f by some constant alpha, then the derivative of this combination is just equal to alpha times f prime c. So basically, multiply a function with alpha, we're going to multiply its derivative by alpha. If you add two functions together, f plus g, then the derivative of this combination is equal to the derivative of the function f as c plus the derivative of the function g as c. So derivative of a combination, of an addition, of a summation is the summation of derivatives. In other words, derivative is compatible with algebraic properties of real numbers. Now the product rule is somewhat different. If you take the product of f and g and differentiate it, then what you get is the following. It is f prime g plus g prime plus f g prime. So the way to remember this formula is that the derivative gonna act on each element in this product. So first, it's gonna apply to the first term in this product f, then it applies to the second term in this product. Now the quotient rule is again a little bit more complicated. So here, this is f prime g minus f g prime divided by g squared. Again, the derivative acts on each term of this quotient, but because it's a quotient, then we had to modify the identity accordingly. Now, next is the chain rule, which gonna be which gonna take us a little bit longer to state and prove. The reason it takes longer is because we want to give a proof this chain rule. Obviously, we could learn the chain rule from a calculus textbook, but in the calculus textbook, it doesn't tell you where the chain rule comes from and why the chain rule is true. In this class about advanced calculus or baby reanalysis, we develop everything from scratch and try to give as many proofs as possible. So the proof of the chain rule basically based on a classical theorem called the Krafft-Serre theorem. It says that f is a differentiable C even only there exists a function phi on I that is continuous. A C and satisfies the property that fx minus fc equal to phi of x times x minus c for all x inside the interval. Furthermore, in this case, phi of c is equal to the derivative of the function f evaluated at c. The proof here is not complicated. In one direction, we just define the function phi as the quotient that arises in the definition of the derivative. Of course, that expression doesn't make sense when x equals to c because you cannot divide by 0. However, you can overcome that difficulty by defining phi of x as c equal to the derivative of the function evaluated at this point c. By what we discussed in a previous section, if the limit of the function exists, we can extend the function in a continuous way, and it applies to this situation. And that's why phi is continuous and satisfies the desired property. In the other direction, we assume that phi is continuous and satisfies all the desired properties above. Then we can relate the expression in the definition of the derivative with this function phi, and because this function phi is continuous, it implies that the limit exists, and as a consequence, the derivative exists at that point. Now, using that Krafft-Serre theorem, we can establish the chain rule. Let ij be intervals and g a function from I to R, f a function from J to R, such that f of J is actually a subset of the interval I. So let me draw a picture here. So here is the interval. Let me use another color for clarity. So here is the interval I. And then you have another interval J here. So the function f actually maps this interval J to a subset of the interval I. This is the image of I. And then you have another function G from I to the set of all real numbers. So this is an infinite interval. Let me use another color here. This is the function G. The conclusion is that if f is differentiable C and G is also differentiable at f of C. So C is the point here, f of C is this point. Then the derivative of the composition G and F is actually equal to G prime f of C times F prime C. So the proof follows from the characteristic theorem above. Basically, the idea is that we can express the difference fx minus fc and gy minus g of d by some function phi of x and phi of y using the characteristic theorem. As a consequence, we can write out the difference of in terms the difference for the composition function as the product of the function phi and psi. And as a consequence, we show that the derivative of the composition function is computed using the product rule is computed using the function phi and psi accordingly, leading to the answer. Here is an example. Let f be a function from some subset A to the set of all real numbers. We consider the function 1 over f. Here we see that 1 over f is essentially the composition of two functions h and f, where h is a function which is equal to the reciprocal of the input h of x equal to 1 over x. And from a previous section, we can compute the limit associated with this function and deduce that the derivative of the function h prime equal to minus 1 over c squared. Then by the chain rule, the derivative of the function 1 over f is the derivative of the composition function h and f, which is equal to h prime f of x evaluated at f of x and multiply with f prime evaluated at x, which is equal to minus 1 over f of x squared multiplied with f prime of x. That is 1 over f prime equal to minus of f prime of x divided by x squared. Observe that we can derive this equation using the quotient rule, but we can also derive the equation using the chain rule. And the reason we would like to learn how to do it in different ways is to give you more tools at your disposal so that you can apply these tools to a future problem. Another example is a function tangent of x, which equal to the quotient of psi of x divided by cosine of x. So here we are given that the derivative of the function psi of x is equal to cosine of x, and the derivative of the function cosine of x equal to minus of the function psi of x. Then we can compute the derivative of this function using the product rule and the chain rule in a very standard way. This is more familiar to what you learn in a calculus class. Now, we discussed how to find the derivative of an inverse function. Recall that a function f from some subset A to another set B, which is a subset of the set of all real numbers. Then the inverse f to the minus 1 is a function from B to A. This function only exists when f is injective. Furthermore, again by a previous discussion, if f is continuous, then its inverse is also continuous. So how does the derivative of this function relate to the derivative of the original function? In order to answer this question, we let G denote the inverse of the function f for clarity. Now we have f of x equal to y, then g of y going to be equal to x. That is, g of f of x is equal to x. So this on the left hand side here is a composition of two functions. That's why using the chain rule to differentiate both sides of this equation, we have on one side we have the derivative of the function x. On the other side, you have the derivative of this composition g composed with f. So the derivative of the other side equal to g prime evaluated at f of x multiplies with f prime of x. So the derivative of the function x is just equal to 1. So this is equal to g prime. That is 1 equal to g prime f of x times f prime of x, which implies that g prime f of x equals 1 over f prime x. And remember, g is just the dummy variable to represent the inverse of the function f. So here we can say that the derivative of the inverse function is equal to 1 over the derivative of the original function. So the theorem here restate that observation in a rigorous way. Remember, in order to carry out this calculation, we need to assume that these functions are differentiable. And so that's why in the theorem here, we have all the necessary additional assumptions. And we can apply this theorem to compute the derivative of the function, which is the inverse of the psi function. So the psi function is strictly increasing on the interval from minus pi over 2 to pi over 2. That's why there is an inverse function denoted by arc psi of y. And here, using the theorem above, we can compute that the derivative of this function is exactly equal to 1 over the derivative of the function psi of x. And the derivative of the function psi of x, remember, that is cos psi of x. So here we have y equals psi of x. Cos psi of x squared is equal to 1 minus psi square of x equal to 1 minus y squared. So cos psi of x here equal to plus the square root of 1 minus y squared. And we have the plus here because cos psi of x is greater than 0 in this interval from minus pi over 2 to pi over 2. So here we conclude that the derivative of the arc psi function equal to 1 over the square root of 1 minus y squared.